Hello, my name is Herminso Villarraga Gomez, and I'm with Size Industrial Quality Solutions. And the topic of the presentation today is assessing lithium-ion cell batteries with 3D X-ray inspection. Let me start with this question. What does the car shown in the picture have in common with a smartphone and a laptop computer? They all use rechargeable batteries as a power source, right? Today, we cannot live without rechargeable batteries. They play an essential role in a world largely dependent on portable electronic devices. What is more, lithium-ion batteries have propelled recent developments and commercialization of electric vehicles. With the recent growth of the battery industry, several intensive research initiatives and coordinate collaborations with universities and private companies are developing solid-state batteries and other cell technologies built with new emerging energy materials. The key difference between the conventional battery and a solid-state battery is that the former uses a liquid electrolyte solution to regulate the flow current, while solid-state batteries opt for solid electrolyte. Solid-state electrolyte enables the integration of better perform materials such as lithium metal and high voltage cathode materials. And they still work in the same way as conventional batteries do, but with the change in materials, there are some battery attributes that change, including maximum storage capability, charging times, size, and safety. Solid-state battery can pack in twice as much energy as lithium-ion batteries. This is because instead of requiring large separators between the liquid cells, solid-state batteries only require very thin barriers to prevent a short circuit. Because most of the work that we do on imaging new battery developments is protected by confidentiality or non-disclosure agreements with our partners and customers, I won't be able to show you X-ray images of solid-state batteries. So let me concentrate on conventional lithium-ion batteries for the purpose of this presentation, but in reality, the very same principles apply in terms of X-ray imaging and non-destructive evaluation. So you can extrapolate on what is possible with other types of batteries. All right, back to basics. The figure shows an illustration of what is inside of a cylindrical lithium-ion battery, the standard 18650 in this case. There is a jelly roll consisting of a negative electrode, the anode, and a positive electrode, the cathode, and a separator in between. During discharge, lithium ions leave the active particles in the anode and travel via the liquid electrolyte into the active particles in the cathode, while the electrons travel through an external circuit to the cathode. During charge, the reverse process occurs. The image on the right side shows micrographs that reveal the spiral architecture of an 18650 battery cell. The yellow layers in the 3D rendering represent the positive electrode, and the magenta layers represent the negative electrodes, each with their respective current collectors sandwiched between electrode layers. The image on the left illustrates the battery manufacturing process, which includes mixing, coating, solvent evaporation, calendering, lamination, and winding in the final stage of battery assembly and electrolyte filling. There are several advanced imaging techniques that can be used for inspecting lithium-ion batteries. There is white light interferometry or visible light, which can be used at higher resolution capabilities, but is limited to scanning the surface of the device. There are also eddy currents techniques and ultrasonic testing, and they can certainly penetrate the part, but have limitation in the achievable measuring resolution. As far as now, the technology that can non-destructively reconstruct the full volume of a battery is 3D X-ray computer tomography, and it can give you image spatial resolutions down to nanometers. There are other imaging techniques that can be used as electron beam, neutron beam, etc., But X-ray computer tomography is the only technique that can non-destructively inspect the interior of battery cells across multiple length scales, from centimeters for cell level analysis to sub-millimeters volumes for microstructure level analysis. Perhaps this might be better understood when you see the resolution of common imaging techniques for lithium-ion batteries and the size of structural features inside of battery cells. X-rays transmits much deeper in battery materials and can capture relevant structural details with a spatial resolution ranging from several tens of micrometers down to tens of nanometers. And from the several types of X-ray imaging technologies, most of industrial solutions for battery inspections are in the realm of macro-CT, micro-CT, and nano-CT technologies, or combinations of them. In the traditional micro-CT world, the main approach is to use a projection-based system that is basically composed of an X-ray source, a detector, and a rotation stage to place the part. The main difference of the so-called X-ray microscopes as compared to the traditional projection-based micro-CT system is that they include a set of lenses that add optical magnification capabilities, additional to the geometrical magnification. This allows submicron resolution capabilities. With the traditional X-ray CT system, it is difficult to achieve that. Projection-based systems are typically limited to resolutions in the order of 2 microns or 5 microns in the best possible conditions for very small samples. But this is not a problem with the 3D X-ray microscopes we have designed at size because we have something called resolution at a distance, which we use to preserve the high resolution of the reconstructed data even for larger samples. The example shows how we can scan a full device as a smartphone without destroying it and then check for small details like the battery cells. By using the zoom lenses using the 3D X-ray microscope, we can inspect the quality of the smartphone battery, looking for any structural changes or degradations in the different layers of the battery, such as cracks caused perhaps by fatigue operations during several cycles of charging and discharging. One of the standard battery sizes for automotive and electronic application is the 18650 format. On the right side of the screen, you can see an image of the inside of a battery, where cracks can clearly be identified and voids and imperfection in the internal structure of the battery produced by aging effects. This level of contrast and detail, of course, is exceptional. Let me see if I can zoom in more so you can see better details. And you can see there here. This level of contrast and detail is, of course, exceptional. And certainly you cannot see this with conventional X-ray CT systems that use flat panel detectors. In this image, you see the reconstruction of a region of interest of an 18650 lithium-ion battery where different layer components can be separated. You can clearly identify and separate by colors the cathode, the anode, and the aluminum and copper collectors. Another off-the-shelf model that you can currently find in the market is the 2700 lithium-ion battery. It has an increase in battery diameter to achieve a higher capacity, providing a power density that is better than that provided by the 18650 batteries. If I'm not mistaken, up to approximately 20% higher. In this video, you'll see the 3D reconstruction of several portions of the battery performed with one of our 3D X-ray microscopes using resolution at a distance in order to scan small regions of interest at high resolution without slicing or cutting the battery open. From the video, you can see several interesting details, such as the presence of particle inclusions in the different interlayers of the battery. And at the end, we were also able to detect a large crack inside of the battery, caused perhaps by fatigue operation. And I think that's what you are going to see at the video right now. By doing segmentation and putting a color in that segmentation, you can see where the crack is. In this slide, you can see how using X-ray microscopy with different sets of lenses and resolution at a distance, images of different resolution can be scanned. You see images of the whole battery with 34 micrometers voxel size, and then regions of interest scanned with 11.5 micrometers, 4 micrometers, and 2 micrometer voxel size. In this image, you can see details not only at high resolution, but also at high contrast, which is often difficult to obtain with the traditional X-ray CT technologies. This is not a problem when you use 3D X-ray microscopes. And you can see low density features in the battery, such as the polymer separator layers that you can see right here. You can see the nice contrast of that image that provides from these regions of interest. The so-called pouch cell batteries are also common in electronic devices and in research applications for prototyping new materials and studying aging effects. In this example, you can see how, using X-ray microscopy, different regions of interest in the same battery can be scanned non-destructively and without cutting or opening the sample to analyze the microstructure of the battery cell. You see images of the whole battery taken with the flat panel, then with the 0.4x lens, the 4x lens, and the 20x lens magnification. The resolution at a distance concept enables 3D image reconstructions taken without removing the sample from the tool, scout and scan to an area of interest, and capture detailed tomographies. Again, let me zoom for better visualization so you can see this at your end. This level of contrast is definitely very impressive. And here you can see more details with the size X-ray microscopes. Special resolutions and voxel size of less than 1 micrometer can be obtained. The image and the video show an exemplary analysis of the internal microstructure of the battery cell, where the cathode and anode particles are resolvable. And the high contrast capabilities of our X-ray imaging tools are even able to reveal low density details, such as the polymer separator layers and bubbles in the electrolyte. I think you can see them here. If not, then I might have a different image in the next slide. Regions of different sections of interest can be selected, as you can see in this image, to see very fine details in the battery without destroying the sample. You can see 2D slices through the 3D cylinder represented in the main image, which can be used to assess, for example, the microstructural changes of cathode material over multiple cycles of charging and discharging the battery. This is important to studying aging effects. Slides from multiple magnifications from different scans can be performed with different objective lenses using the 3D X-ray microscope, and then overlay one on top of the other for better comparison and better visualization. The overview scan can differentiate different materials, even soft materials, as you can see in the image. For example, you can see the bubble electrolytes that I just mentioned, and I think they are right around here. Yeah. With this type of details, you can instruct battery wetting processes or outgassing effects during aging, and the resolvable pale squiggle that you can see in the polymer battery separator as it is stained into the pouch from the boundary between the anode and the cathode. Again, resolving this level of details is very impressive. This is very difficult to obtain with a traditional X-ray flat panel detector, but it's not with our 3D X-ray microscopes, because we have a resolution at a distance and optical magnification. There are obvious dense structures of the cathode and electrode that you can see, like the thick white bands, the anode current collector, the white stripes, and battery pouch casing, the perimeter, which all are detailed in this image. But the most impressive part is, of course, zooming in to see the granular microstructure of the graphite anode, as well as the mixture of lithium cobalt oxide in the cathode. You can clearly notice anode and cathode microstructure that is giving you very resolvable features and even trails of delamination in this image. Here we show the outcome of poor mixing and weak battery calendering compacting process. Cathode particles are spaced too far apart in the image that has the low pressure. So you can observe some voids and binder material. The two cathodes shown in the video have been compressed at different calendering processes, resulting in difference in the density of the cathode, also particle packing and porosity in the resulting electrode, potentially affecting the electrochemical performance of lithium-ion battery cells. The low density of cathode materials will be reflected in a suboptimal energy density, which will be experienced by the user as a poor charge capacity in their device. This image shows typical changes in the microstructure of silicon particles of graphite battery anode with aging. The silicon anode particles from this image can be identified by shape and contrast, and after aging 200 cycles, we can see that the silicon is almost completely gone. This was an unexpected result, so we repeated the measurement, this time with 100 charging cycles. And you can see we found a broken, cracked silicon particle, which was pushed away the graphite around it, and you can see it clearly right here. These are very interesting details that we can observe with 3D X-ray microscopy techniques. Observing this in 3D with the Zeiss X-ray Versa microscopes, we can see exploding silicon particles in the anode electrolyte. There is an expansion of the electrode structure during the charging, and this is very hard to detect with traditional electron microscopes or light microscopes. And even if you use those, you will have to slice the battery or destroy it. We can observe the particles using the 3D X-ray microscopy here, and we can clearly see what is happening. The void and byproduct materials around the silicon particle are clearly seen and observed here. This video shows a non-destructive comparison of the microstructure of a one-cycle charge versus 80 cycles, where you can easily see morphological changes, mechanical deformation at the edges of the electrolytes, stress formation, and some variations of the radial distance and separation of different interlayers in the battery, as you can see in the top. And if you want to learn more about the topic of diagnosing and correcting anode-free cell failure via electrolyte and morphological analysis, I would recommend you to check out papers that have been published recently in Nature Energy. And this other one published in Nature Communication, in which you see they use the Zeiss Ultra X-ray microscope, and you can see high-level details like you can see in this one. So just check the paper for further learning. This is an image of the zoom-in X-ray images from the previous slide, and you can see the reconstruction that are obtained, typical reconstruction that you could obtain with the X-ray Ultra microscope. This video shows this kind of a small portion of the battery performed to see fine details down to nanometers resolution. You can see some internal particles that are split in two or more pieces, and you can see cracks in them. So this is very interesting. All of these 3D X-ray microscopes are part of a larger set of multi-scale correlative microscopy tools, which include microscopes capable of delivering spatial resolutions down to half a nanometer, with the Lithium-Ion microscope, for example. With 3D X-ray microscopes, we can go down to spatial resolutions in the order of 50 nanometers. Multi-scale correlative insights into the battery performance and safety can be obtained from centimeters to nanometers with X-ray computer tomography and microscopy. And to summarize the content that have been discussed today, thanks to the integrated Zeiss quality assurance portfolio, we can connect all data from light microscopy to electron microscope and X-ray micro-CT, and even optical and tactile coordinate measuring machines. X-ray quality assurance solutions can be obtained from material research to battery production, in-line and at-line quality control or failure analysis to inspect anode, cathode, separator, raw materials, electrolyte production or electrode production, cell assembly, module analysis, and even battery packs for all kind of defects that you can check here or things that you can imagine that you can inspect. In a module assembly, typical inspection workflow check for overhanging, metal inclusions, cell defect, welding defect, electronic components quality, and housing integrity. This is another example that additionally inspect the upper tab integrity, the electrode damage, voids, and even delamination. So there are X-ray image applications in battery manufacturing at the research laboratory and at line production for both quality inspection and failure analysis. As always, with the size X-ray series, we make the invisible visible. And we have many other industrial quality solutions. So please visit our homepage at SAIS to see our full portfolio. Typical markets and applications that we serve are automotive, aerospace, medical devices, electronics, additive manufacturing, and many others. Solid state and lithium-ion batteries find application across multiple industries such as electric vehicles, energy storage, consumer electronics, aerospace, and other industry sectors. So with this, I want to finish my presentation for today. And if you have any questions, I'll be happy to answer.